Hey everyone, this is the Unit 1 review video and I'm going to do some select problems to hopefully help you prepare for the test. You can find the other solutions on Canvas. I'm just going to work a few to kind of give you an idea of one of each type of problem. So starting with number 1, the figure above shows the graph of a function f with a domain between 0 and 4. Which of the following statements are true? So this asks for the limit as x approaches 2 from the left of f of x. So that does exist. We can see that there's some y value there, so that is true. The limit as x approaches 2 from the right of f of x, we can see is also some number there. That does exist from the right. The limit as x approaches 2 of f of x exists. Well, because we can see whatever this left number is and this right number would not be the same. The limit at 2 would not exist. From the left and the right, we could get a number, but not for the actual value of 2. So our correct answer would be, which is true, 1 and 2. C. Okay, number 2. For what values of a does the limit as x approaches some a value of f of x equals 0? So we want to know where the limit equals 0 on this graph. So let's look at 2. At 2, the limit is 0. We can see from the left and the right at 2, it would equal 0. So that's true. At 2 or 4, we already know 2 works. How about 4? 4, the limit would also be 0 because I can see from the left and the right, it is approaching 0. So that is true, which makes that not true. How about at 0? At 0, we have a jump discontinuity here. From the left, it's going to be 0, and to the right, it's going to be -1. So 0 doesn't work, 0 doesn't work. B has to be our correct answer. Okay, I'm skipping to number 5, since the other ones were more of the same kinds of limit questions. So we're trying to find a true statement here. So f of a equals 2. So that's telling us there is a point, a, that the y value is 2. The y value is actually 1. So that is not true because that would have to be a 1 for that point. F is continuous at x equals a. Well, that's not true because we have a hole right here. If that point was there, it would be continuous. So it's not continuous. The limit as x approaches a of f of x is 1. Also not true because it looks like this is approaching 2 there, right there. The limit is approaching 2. The limit as x approaches a of f of x equals 2. We just said that that was true. And the limit as x approaches a of f of x does not exist. We already said it's at 2, so that makes that not true. If yours got cut off, I think it's supposed to be a as x approaches a since that's the point we're talking about. So D is our correct answer. Okay, these are a bunch of the limit questions, and I'm going to just skip down to the infinite ones because I feel like those are the ones that are tricky. So this is just asking on the graph, as x is approaching negative infinity on the f of x graph, so negative infinity is this way, okay? So what is the graph approaching as we go towards negative infinity? We can see this graph is swooping down and getting very, very close to 0. How about positive infinity? Same idea. When we look at this graph, when we go towards positive infinity, the graph is also getting very, very close to 0, just from the other side, but they're still approaching 0. This indicates we probably have a horizontal asymptote here at 0 for this function. Okay, section 2 is finding the limits algebraically. Thus far, we were just doing the graphs. So your first thing you should always try is to plug in. That's step 1 anytime you're doing it, because sometimes when you plug it in, that's all you have to do and you're done, okay? If you get indeterminate, so that means 0 over 0 or infinity over infinity, then you want to try to rearrange it in some way. You can try factoring, you can rationalize it to see if you can get rid of the radical. Try one of those things to see if you can get it to then be able to plug in. So let's try a couple examples. I'm going to try 23 first. So we're always going to try plugging in first. So this is asking us to figure out 3 pi over 2. If I plug that in right there, think about on your unit circle where that would be. So we've got a half pi, whole pi. 3 pi over 2 is this one that's straight down. So the coordinate there is 0, -1. So cosine is 0 there. So 0 minus 2. Sine, that point down there, here's what we're down here, 0, -1. So the sine value is -1. -1 minus -1 is -2. So this equals 1. So we didn't even have to rearrange that one. That's an example of just when you plug it in, it works out. You don't have to do anything special. Now let's look at 22. When I plug in 9 here, I get the square root of 9 is 3. 3 minus 3 is 0. And I can already see this is going to be 0. This is an example of the indeterminate. When I plugged it in, I got 0 over 0. So what we want to do is we want to use one of our tricks to try to be able to plug it in. So rationalizing is when we have a radical here. So I'm going to multiply this by square root of x plus 3. That's the conjugate. You always change the sign of that. Square root of x plus 3. And now, when I multiply this out, square root of x times square root of x is x. This is going to be a negative, and this is going to be a positive. Those will cancel out. -3 times +3 is 9. And I'm going to leave my denominator. Oh, actually, that should be a -9. Okay. I like to leave my denominator because a lot of times it cancels out anyways. We can always do something later. See how these cancel right away? So that really does help us. So now only thing left on top is a 1. So I can try plugging in my 9 again. So I have 1 over, I'm going to plug in 9. Square root of 9 is 3. Plus 3 is 6. So see how rationalizing to get rid of the radical helped us be able to now plug in our limit number, our x value there, and get a solution. Okay, anytime you see an infinity, we're looking towards the graph's endpoints, like infinity or negative infinity. This always means you're looking for the horizontal asymptote. That's always the case when you're looking for as x is approaching infinity. So to find the horizontal asymptote, we ask ourselves, is this top heavy, bottom heavy, or the same? Well, I see I have x to the 5th on the top and x to the 5th on the bottom. Those are my highest degrees. And they're the same. So when they're the same, we divide the leading coefficients, which means we divide the numbers in front. So this means -2 divided by -3 is 2/3. So my limit there, as we go to positive infinity, the graph is going to approach the horizontal asymptote that is at 2/3. Okay, skipping down to number 28. Okay, we have another infinity here. So we know we're looking at the horizontal asymptote. So I'm looking at the top heavy, bottom heavy are the same. So let's see, in the top, it's x squared. In the bottom, it's x squared. Dang, I meant to get a different problem, and that's the same kind of problem, isn't it? So they're the same, which means 5 over 10 is going to reduce to 1/2. So my limit would be there. Let's look at 27 as our last example. Okay, when I plug in 0 here, I'm going to get 0 over 0. So this is another example of the indeterminate form. So we always want to try to factor it to see if we can rearrange it and find a way to plug in that 0. I see an x squared in all these. So if I have an x squared, okay, I factored out an x squared and I took out an x squared here. I took out a GCF because then I noticed I could cancel that. And now I'm going to try to, I shouldn't put equals there. The reason I should put equals is because unless I'm going to rewrite this as a limit, that limit now equals that limit. Okay, just trying to show y'all proper notation. So when I plug in 0, 3 is on top, 0 plus 5 is 5. So my limit as x approaches 0 of this is 3/5. Alrighty, this is about, section 3 is about continuity, and I'm going to skip down to part B as the example. Anytime you see continuity on the test, you need to make sure and think about the full definition. There's 3 parts. Remember, does the point exist? Does the limit from the left and the right match? That means the limit exists. And does the point equal the limit? Those are the 3 things that you have to prove when you're proving continuity. So we're looking at where x is 2. That's this piece right here. And I'm looking at it, and it's not continuous because I have a hole here, right? So now I have to use my limit definition to prove it. I can't just say, well, it's discontinuous because there's a hole. That's what you learned in pre-cal. In calculus, we have to use our limit definition. So start with part 1. Part 1 says, does the point exist? Well, yes, f of 2 equals 1. Part 1 of the definition is correct. Part 2 is, as x approaches 2 from the left of f of x, that is 1, 2, 3, 3. And the limit as x approaches 2 from the right of f of x is 3. So yes, the limit does exist because from the left and the right they match. Okay, so that's important. The limit as x approaches 2 from the left equals the limit as x approaches 2 from the right of f of x. So you don't have to write both of these out as long as you say they match. You definitely want to say that they match each other. The left and the right match, therefore it's we've now proven that the limit exists. The third component is, do they match? Okay, the limit as x approaches 2 is not the same number as f of 2. Therefore, f of x is not continuous at x equals 2. Be very explicit in your description here and your good notation on your free response questions. Like, I'm treating this as like an FRQ question. I'm showing every step. I'm showing good limit notation. This is one thing that's going to be very important in AP Calculus, is really demonstrating that you have good notation and a good explanation. So really practice it until you've captured all of those pieces. I'm looking for all 3 of those parts to get full credit on the FRQ there. Okay, these next 2 are basically finding the missing pieces. Find the value of k and find the value of p here. And we're wanting to make this function continuous. We have a piecewise function here. So the key part we're trying to see is if it's continuous at 1, because we know a quadratic is continuous. Both of these are quadratics. But what happens at 1? Do they match up? So I'm going to start with, you can start with the point or the limit. I'm going to use the limit. The limit as x approaches 1 from the left of this f of x function is, here's my left side, 2 times 1 minus 1 squared. 2 minus 1 is 1. The limit as x approaches 1 from the right. Okay, so this is my right side of the piece. So 1 squared plus k times 1. So 1 plus k plus p. Oh, they gave me the k. It's 2 right there. I was like, how am I going to do it with this many variables? Let's see what we're doing now. 3 plus p. Okay, in order for it to be continuous, my limit from the left and my limit from the right have to match. So 3 plus p has to equal this 1, which means P has to be -2. So you can do it from the point, but for sure do the limits, because the limit from the left and the right have to match. So that would be the minimum, and then getting the value there. Okay, number 33. Find the vertical asymptote. Vertical asymptote, always think about the denominator equal to 0. So my vertical asymptote here is going to be x equals 2. When I set that equal to 0, it would be 2. My horizontal asymptote, we always think top heavy, bottom heavy are the same. Since these guys are the same degree, we're going to divide the leading coefficients. And so the horizontal asymptote is going to be 3. Oh, and then it's saying find A plus C. Oh, we're just adding them together. So that would be 5. Okay. Skip a couple down. 39. What are the equations of the horizontal asymptotes of the graph of y equals 2x divided by the square root of x squared minus 1? So this is the question whenever we're looking for the horizontal asymptote. Is it top heavy, bottom heavy, or the same? This one is technically the same because when I take the square root of x squared, that gives me an x. That's a degree of 1, and this is a degree of 1. So when they're the same, we divide the leading coefficients. So that's going to be 2 divided by 1. Now because I have a square root in here though, it's always going to be plus or minus. So my horizontal asymptote is going to be y equals, it's going to be positive and -2. It's always interesting to look at these in the graphs. If you put this in Desmos or in your calculator, you'll see that it does some funky thing where on this side maybe it's approaching +2, and on this side it's approaching -2. So there's probably 2 horizontal asymptotes in this one, and as it approaches negative and positive infinity, you'll get to see that we're having those 2 horizontal asymptotes. So with the square root, it's always plus or minus, okay? And then we're just dividing those leading coefficients. I know those are the tricky ones. Okay, I'm skipping to number 40, I believe this is. Yes, 40. Here's the function. The figure above shows a portion of the graph of f. Which of the following could be the values of the constants a and b? So we're looking to find these. Well, we know the denominator is about the vertical asymptotes. We have a vertical asymptote here at 2. I also see this squared. So I'm kind of thinking like I can't see what's over here, but to me this triggers a difference of squares kind of factoring problem. So I'm thinking like this would be x squared minus 4 would be my denominator, so that I would have a vertical asymptote at 2 and -2. So I'm thinking for b, my b is going to be -4. The horizontal asymptote is top heavy, bottom heavy, the same. They have the same powers here. So that means I'm looking at the coefficients in front. Well, the coefficient in front of here is 1. So if I have a horizontal asymptote here at 3, 3 divided by 1 is 3. So this means my a value has to be 3 because of the horizontal asymptote there. Okay, last section in IVT. This was the intermediate value theorem. And we talked about some problems like this. Explain how you know the graph of q of x crosses the x-axis at least once. If it helps you to kind of draw a picture to visualize this, sometimes it helps you see why it has to cross at least once. So at -2, -9.6, we have a point. At -1, we have a value at -6.4. At 0, we're up here at like 2.7. At 1, we have something at 3.4. Okay, I realize this is not to scale. I just wanted to show if this is continuous, if q of x is continuous, you can see it's got to cross somewhere in here because we've got negative values down here and positive up here. So how do we know? Because q of negative 1 is negative 6.4, and q of 0 is 2.7. Yeah. And since 0 lies between those 2 points, and q of t is continuous by IVT, q of x must cross the x-axis, sorry, this is getting long, at least once. Let's just talk about the key points. Whenever you use IVT, you have to have two things. One, maybe three things. I was going to say there's two conditions that must be met. You must say it is continuous somewhere in your thing. I'm going to be looking for that word. I'm also going to be looking for the points that you said it falls between. It falls between this point and this point. I'm looking at, these are the two conditions that must be met in order for you to use IVT. Okay, so make sure you have the conditions met, and then your conclusion. By IVT, yes, it must cross at least once. So I'm looking for some kind of affirmative statement saying, yes, it does cross at least one time. Okay, 42. I think this is my last one. This is another IVT problem. F of x, so they're saying, is there a y value that equals negative 3 has a solution in 1 to 8? So all of these are talking about this table between 1 and 8.